All right. Good morning, everybody. Nice to see still so many. It's that early in the morning. So welcome to motion planning, the third lecture. Last week we didn't have a lecture, so I will spend some time recapping at the beginning, and then we will dive into graph-based planning and various algorithms, including the A-star algorithm, which you may or hopefully already know. Okay, so last time, about 2 weeks ago, we basically wrapped up the foundations of motion planning. So we looked at the definition of how can we formulate geometric and kinodynamic motion planning problems. And then we looked at the configuration space and joints for manipulator robots, topological spaces, how we can measure distances in these sort of spaces using metrics. And then finally, how to deal with constraints, and also how can we do efficient collision checking, since that is one of the major constraints that we have to fulfill. And so today we are looking at basically the first class of algorithms to solve motion planning problems. Specifically, we are looking at solving geometric motion planning problems using graph search algorithms. And so the motivation behind that is that we can represent a robot as a point in our configuration space. That is kind of what we also learned last time. And that configuration space is potentially very high dimensional. So for some robots, it could be more than 10 dimensions. And then the motion planning problem is nothing else, but as input, we get some sort of description of our robot and our obstacles. We get a start configuration and a goal configuration in that configuration space. And ideally, we get out some sort of description on how we get from the start to the goal. And in the geometric planning problems, there would be a path. And the kinodynamic problems, there would be a motion, which means a sequence of states and also actions. And so formally what we had was this configuration space. We called this calligraphic queue. We had this kind of free space and obstacle space. Sometimes we also defined it in the free workspace and obstacle workspace to figure out where our constraints are. Then, of course, we require that our initial and final configurations are in the free space, so not on top of an obstacle. And the solution is this sequence, which we can either formulate as a function that gets as parameter the kind of time or progress variable, and then returns our configuration. Or in practice, it's often a discrete sequence of configurations that define our path. And then what we are typically interested in is algorithms that are at least complete. And by complete, we mean that if a solution really exists, the algorithm should eventually find it. We are also often interested in optimality, and we will talk about that in the context of A-star. Okay, and so one classic approach to solve the problem is now, of course, we can try to find some sort of graph representation of the configuration space, and then once we have that, we can compute our solution. And so before we kind of dive into that, let me briefly discuss some, let's say, older methods that are at least interesting for the geometric case to consider. And so in total, we will discuss these kind of mapping-based approaches, cover-based approaches, and then finally the graph-based approach, and then we will kind of stay on the graph-based approach. So for the mapping-based approach, the idea is that we try to map all of these obstacles in the configuration space into some sort of discrete cells, and then we look at how we can connect these cells. Also, you can almost think about it like a graph, but instead of having like zero-dimensional vertex, you have these cells that take up the volume. And it turns out that that kind of approach is pretty old. So in the 90s was developed. And here's kind of an example picture. So what we have is on the red is the robot that can kind of rotate around these axes and then also move. So the black dot is kind of the center of mass. And then this gray thing is some sort of obstacle. And so what we want to know is how does this space actually look like in this case? And so we have to consider all the different orientations. And so here they kind of discretized the orientations between 0 and 180 degrees. And then you get these kind of neighboring, almost cell-like structures, and then you can try to find a solution by going from neighbor to neighbor. Very similar is kind of the cover-based approach, which is slightly newer, I would say. So you can also find it in that Laval planning book. And here the idea is to use a different sort of description on what open space means. So you use very simple geometric shapes that kind of cover the space that is free. And then you try to find a solution by connecting these spaces. And so that's also visually much easier to see. So let's assume as geometric shape we use a circle, just because fitting a circle into these sort of geometric problems is fairly easy. Then you can put a bunch of circles, some of which overlap. And then your goal in motion planning would be just to find these circles that kind of overlap and find a sequence that maybe has some sort of lowest cost, right? Of course, one can imagine that figuring out like how to place the circles is not entirely trivial and also not unique. So there's many ways of doing it. And so I would say in all of these approaches, it's already pretty close to this graph-based approach where we say we try to identify some sort of graph that has locations and kind of connections. And that graph should capture more or less what is going on in our free space. And then we can use any graph search algorithm to kind of reason over that description to find solutions. And so an advantage is that the other two approaches kind of work fine in 2D. Some of them are okay in 3D, but it becomes more complex because you would, for example, for the cover-based approach, you would need to fit spheres. And in practice, these days, these approaches are not used anymore. And instead, we mostly use graph-based approaches if we are within the search-based motion planning domain, which we discuss today and next week. And so in the rest of the lecture, I just want to focus mostly on this graph-based motion planning. And we have kind of two parts we have to look at. The first part is how can we even find a graph and describe it? And then the second part is how can we now use the graph in order to do something useful for our motion planning problems. Okay, so let's first talk about the first aspect, which is how can we represent graphs such that they are useful for motion planning. And so the first, like we have to look at different variants on different axes. And the first one is that how is the graph even stored in memory? And there's an explicit and an implicit representation that we will talk about. And secondly, independent of how it's stored, it's how is it being constructed based on the description we might have of the environment. So let's first look at what is happening in the memory. So for explicit graphs, we quite literally have some data structures that could be a list of vertices and a list of edges. The vertices correspond typically to a configuration, which means in 2D it would be just a 2D point, for example, for a simple robot. In higher dimensions it would be basically a vector that represents our configuration. And then the edges just kind of tell us which vertices are connected. It could be an undirected graph or a directed graph. For the memory representation, it doesn't really matter. And so we can, of course, write it down explicitly. And an implicit graph instead just has one start state and some sort of functions that we can query. And that function gets a state as input and returns a set of successors as output. Okay. So here's basically already what I said. So maybe just in terms of notation, what's important is that typically we call the graph G, and then G is a tuple of two sets. The first set is the set V, which represents all the vertices. And the second set is E, which is typically also another tuple, which maps like two vertices that are connected. Okay, and then of course once we have this explicit graph, we can use any algorithm to search over it. That's not really magic. And now the implicit graph, we just have this successor function, which means the search is slightly different because instead of now looking up in our data structure what our neighbors are, we have to call the successor function during the expand operation to find the best node. Okay, so do you have any ideas what might be advantages and disadvantages of these two approaches? Yes?
I would imagine that the lookup of successor in the explicit graphs is faster because it doesn't need to be computed on the fly.
Exactly. So specifically the lookup could be, for example, like a hash map, and then it's constant time. Yes?
Yeah, maybe if I want to search for a specific vertex, I don't have to iterate over the whole, create the whole graph with a graph function. I can just search the list of vertices.
Very good. So for example, if our start location changes, we can still use the same graph and immediately get going, right? So that sounds like explicit graphs mostly have advantages. Can you think of a disadvantage?
If we have
Sure, go ahead.
If we have infinite vertices or edges, we cannot represent it as explicit graphs.
True, but it sounds very abstract to me. So what would be the case where we have infinite vertices?
Like if we have infinite workspace, like if our space is continuous, we can have so many configurations points, and we cannot represent it as discrete points in the graphs.
Exactly. So open workspaces, and that's kind of important because many of kind of the almost more popular algorithms that we study later in the class that are random based or sampling based, they always require a bounded workspace. So it's quite powerful that if we use these sort of implicit graph representations, we can really search over almost infinite spaces and still stay optimal. Okay, so I think now we have everything, and then I wrote down here high memory usage as a disadvantage. That of course depends on how big the graphs are, and that depends on how many dimensions our configuration space has and what kind of the average branching factor is, which means how many neighbors on average does every node have. Okay, then we discussed how we can store a graph. And now the question is, how can we construct it? And there's many different ways, which I briefly want to kind of go over. And again, some of it is a bit more, I would say, historic. It's like interesting to think about it, but it's not that much used anymore. And then we discuss at least 2 or 3 different methods that are actually still actively in use. So a very classic method is what is known as the visibility graph. So the observation here is that if you are in these very simple geometric workspaces where you can represent all of your obstacles as a polygon and your robot is just a point and you want to go from start to the goal, then it turns out that the shortest configuration will always kind of go around some vertices of our obstacles, right? Like here we hit this kind of boundary or corner point of this obstacle, and over here this. And that is always the shortest path. So it would kind of make sense to try to construct a graph that represents all these different options that one could have. Right, so in this example, we really try to just connect all of these different vertices if that is possible, right? Like for example, we could try to connect this point and this point over here, but then the straight line path would go through an obstacle, so we don't add it to the graph. What we do have though is also edges that are exactly at the boundary. For example, we start from here to here. It's a bit hard to see, but there's an edge that connects those two. This is pretty compact. We can construct it in quadratic time, where m is just the number of vertices of our obstacle representation, which is great. So what do you think are advantages and disadvantages of this method? Yeah.
I think it could be disadvantageous if you're always so close to the obstacle.
Very true. So if we don't have this point robot assumption anymore, then it's questionable how useful the result is. Yeah.
Well, if you represent complex obstacles with many vertices, it becomes like very high effort to calculate the graph.
Exactly. So imagine you don't have those polygons, but maybe 3D meshes that are used in games or graphics. And this is not really feasible because you easily have in the order of 10,000s of vertices for these sort of meshes. Yes, and I think for non-polygon obstacles, it's unclear how to do it. And then, of course, maybe we didn't discuss it yet, but it really only works if we have this explicit representation of our environment, which sometimes is like an okay assumption and sometimes not, right? Like, for example, I think 2 weeks ago you learned about Octomap. That was one representation where you can directly take robot sensor readings into account, and the output is something that explicitly defines where your obstacles are. So it's not a totally crazy assumption, but it's not true in general. Okay, then another more like historical thing is the idea of a Voronoi diagram. We will study this Voronoi decomposition a little bit more in detail when we talk about sampling-based algorithms. But in general, what a Voronoi diagram is that it kind of tries to assign regions that are equidistant to some boundary points. And so here the idea is that we create a graph where the points are equidistant to obstacles. So for example, if we look at this vertex here, that's roughly the same distance to this obstacle, this wall down here, to that wall down here, and to that wall up here. And that's true for all the points you have in this graph. Right, and so that one is nice, you can construct it. Then if you have a different start and goal vertex, you just add these vertices to the graph and just connect it to the existing vertices or edges, and you can do your search. And so in this case, the great thing is now we stay away from the obstacles. It actually does work if we have not an explicit representation of the environment, but for example a point cloud, as you would get from an RGBD sensor. But the downside is that, of course, the results are kind of fairly suboptimal because you try to stay far away from your obstacles, which is not so great. And it's also very unclear how to really construct it in higher dimensions. So these Voronoi diagrams were pretty well in 2D, they are okay in 3D, and then afterwards it's not so easy to construct explicitly like that. Okay, and then maybe the most popular method is what is known as a probabilistic roadmap, or PRM. So here the idea is that we use random sampling to identify the vertices. So like that, every time we sample some point, we check if it's on an obstacle or not, and we only keep the vertices around that are not on an obstacle. And then we just connect with different techniques neighboring things. And we will discuss in more detail later what does neighboring mean and what are kind of the different ways of doing these sort of connections. But like before, for each connection, we make sure that the resulting edge is collision-free. So for example, the connection from here to here doesn't work because it would pass through an obstacle. And so here, kind of the great thing is that we can use an implicit representation of our environment. We can fairly quickly discover connected components. And also because we don't need this explicit representation, it works with arbitrarily shaped objects. So even if you have meshes, it's not really a problem as long as you have a reasonably well-working collision checker. And then we discuss also how to maybe partially overcome these kind of problems. But one major challenge is that if you have a narrow passage, it's actually not that likely to end up with samples that go through the narrow passage. And there's kind of some tricks around it to make it work. Okay, and then finally, there's a version of this which doesn't use a generic graph, but a special form of a graph, which is known as a tree. The tree just has basically one root node, which would be at the start, and then it can have multiple successor states at every node. Yeah, so it's still a graph, but it can't have any cycles. And there's versions of these planning algorithms that try to grow the tree in order to find a solution. And we will basically look at that when we talk about sampling-based algorithms. Okay, so that's everything about this skeletonizing our workspace. And the second approach would be to do some sort of cell decomposition. And so the maybe easiest thing is to do these connected grids. So the idea is that we just overlay over our workspace some sort of kind of grid where each of these cells has a finite volume, and then we can actually convert it to a graph. So if you imagine that each of these grid cells becomes a vertex, and then if there are neighboring vertices, then you add an edge. So in this example, you get the following graph, where from S1 to here, there's no vertex and no edge because this vertex was not collision-free. And we kind of distinguish two different versions that are popular in 2D at least. So as a 4-connected grid means we only take the 4 cardinal directions as neighbors, and the 8-connected grid also allows diagonal connections. This example is an 8-connected grid because we allow this connection from S4 to S3. And of course, this also works in principle in 3 dimensions, but you can imagine that the memory consumption is quite high in 3 dimensions, especially if the grid cells are small. Okay, and so here basically the advantage is that it's fairly simple to implement. It also deals with arbitrarily shaped objects. It is very fast to construct, but it scales really poorly with a number of dimensions. So it's basically exponential in the number of dimensions. So just as an example, let's say we have 2D and we like x and y, and we discretize both x and y in 100 kind of cells. Then we get 100 times 100 different cells that we have to consider. But then if we go to 10 dimensions, it would be basically 100 to the power of 10, which is an insanely high number. And so in practice, this sort of thing is done a lot, but mostly for 2D. Already in 3D, you have to typically do some tricks to get it to work. Okay, and then second cell decomposition idea is lattice-based graphs. That is basically a generalization of the grid-based approach. So the idea is that instead of just allowing these cardinal directions, we really also consider how a robot can move. So if we have a car-like robot, it can't really move sideways like that, but it might be able to do differently sharp turns. And then if you're kind of smart about it, you can construct a graph by just connecting these different short motions such that individually the states or vertices represent valid states, and the edges really represent some possible motion that the robot can do. And we kind of look at that next time in more detail, because that is mostly relevant for kinodynamic motion planning. And today we want to focus on geometric motion planning. Okay, so just to kind of wrap up on how we can get these graphs. So the basically current version is that we really try to construct graphs either explicitly or implicitly, and that we use something like probabilistic roadmaps or the cell decomposition to generate this representation. Okay, perfect. So that brings me maybe to the bigger topic of today which is what to do once we have the graph. Do you have any questions about constructing the graph? All right. Okay, so let's start very basic with uninformed search. So who of you has heard of DFS, BFS, and Dijkstra before? Okay, basically almost everyone, I hope. So that will be then just a brief recap so that we're all on the same page. And this one is known as uninformed search because it just uses the current cost from your start to wherever you are, but no particular estimate to the goal. Okay, so DFS, how would that look like for a graph or a tree like that?
We'll go first into the next layer, and then next layer, and then next layer. If we don't find a solution, then go back to the previous layer, and then search back to the other.
Exactly. So we kind of first go very deep, and then when we're at the end, we do this sort of backtracking operation. All right, and then what about BFS?
You just search through the first whole layer and then the second whole layer and then.
Exactly. So we try to cover the breadth first until we have found everything. Okay, what are advantages and disadvantages of BFS versus DFS? Like, when would you use which one? Okay, nobody would ever use it. That's also fine. I mean, in general, if you have some idea where your solution lies, if it's kind of not so far from your starting point, BFS tends to be better. If it's somewhere deep, then maybe DFS is better, right? But in general, we don't use it much because we prefer informed search. And so just to motivate you for informed search, so let's assume you want to maybe travel or fly from Berlin to Tokyo, and there's no direct flight available, and you have to do some sort of hop. Which of these choices do you think would be best to fly first to? Maybe Beijing?
Seoul is the nearest city from Tokyo, so maybe Seoul.
Okay. Exactly. So we kind of is that nearest city. So we kind of look at the distance, how much would be left, assuming it's maybe equal price or whatever to go to these first cities, and then we end up picking the one that has the lowest estimated distance left to get there. And that is exactly the kind of idea of this informed graph search. Right, so we try to inject some sort of knowledge, the information, and then use that information to search a little bit more efficiently and not as blindly as we would do in DFS or BFS. And so the most kind of famous and also most basic algorithm is the A-star algorithm. So who of you has learned about A-star before? Perfect. So also almost everyone. Who of you has studied why it's complete and optimal? Okay, that's fewer people. Or you're too tired. But so basically, again, today will be then a recap first on how the A-star algorithm works, so everybody is on the page, on the same page, and then we also try to go a little bit through the proof of the properties, and the reason for that is that we later also want to look at proofs of maybe some other algorithms, and it kind of makes sense to study the basics first to then see the relationship, maybe how those sort of properties can be shown. Okay, so the A-star algorithm is quite old. So it's from 1970 roughly. It is pretty popular now also in textbooks. So most of maybe the study doesn't really come from the paper, but what we do today in the lecture is still mostly based on the paper. So also the proof, if you want to see later more details, I recommend looking at this very old paper. And maybe that's also important because as part of your grad school education, you want to more go to primary sources and not secondary sources like books if you learn something. Okay, So maybe as motivation, what's cool about A star is that it has these really nice theoretical properties. So the first one is known as completeness. So if a solution exists, it will find it. It even has a nicer property, which is if no solution exists, it will also tell you about it. And completeness is not always defined like that, but A star can do that for finite graphs. It's also optimal, so once it returns a solution, the first solution it returns will be a solution with the lowest cost, and one can define cost almost arbitrarily as long as it's non-negative. And then maybe what's lesser known is that it's also optimal efficient. So one can formally prove that there's no other search algorithm that is given the same information, in our case the same kind of information that we look at, that can produce a better result. By better we mean doing fewer kind of lookups in the graph that we give it. And that makes it really powerful because it means we can stop doing kind of research on graph search, so to speak, at least on this basic variant. It turns out that there are many kind of interesting variants of A star that are highly relevant for robotic motion planning as well. And next week we will study some of them. And so it's kind of important to understand A star because it is the foundation of most of the other versions that are maybe more exciting and you haven't heard before. Okay. And so what we will do today is we first talk a little bit about the notation and data structure, then the pseudocode and run it through an example, and then we do the proof of optimality. And so hopefully the first two topics at least will be just a refresher for you. Okay, so let's start with the notation and data structure. So as before, we are assuming that we have some graph which is represented as this tuple of vertices and edges. And what's new here now is also that each edge has some cost associated with it. And the cost has to be non-negative, otherwise it doesn't really work. We are also giving a start node and a goal node, and those are basically elements of the set of vertices that we are giving. And in principle, A star works for both the explicit and implicit graph representation. So you either give it that G directly, or what you can also do is you give it the successor function, and then you kind of implicitly look it up. And of course, the combination is also possible. If you have an implementation that only works with the successor functions, then you can use your explicit representation to very efficiently define the successor function. So it's almost identical, and the more generic version is that one with the successor function. Okay, and then we have some other important terms. So maybe I start with the cost to come. So the cost to come is the cost of the optimal path, so the lowest cost path, starting from our start node S to that node N. So it's kind of a function that takes a vertex's input and returns typically a real value or an integer value that's positive. Then the cost to go, which we also call often h of n, is the heuristic function. And that is the cost of the optimal path starting from n going to our goal location t. And then the total cost f is the sum of the two, basically constrained on that we go through n. Okay, so let's say we do it graphically. We have some graph here. It's a real graph now, not a tree. We have our start node, our goal node. We have our intermediate node n. And in this case, the graph is directed. So we can't really go traverse the edges in both directions. Then the cost to come would be, in this case, just the cost from S to N, which is the sum of these two kind of edge costs that we have as part of the input. And then the cost to go, H, would be, in this case, also uniquely defined as the sum of these two. If there would be a second pass, it would be the cost that is lower over the two options that we have. And then the total cost is just the sum of the two, constrained by the facts that we want to go through N. Okay, and now in A star, basically the problem is that this term H is not really known, so the heuristic function. Remember that this is like the true cost to go. And because H is unknown, also F is unknown because it's part of the equation. And so instead what we do is we try to use this H hat, which is an estimate of the true H function. And then H hat is typically termed the heuristic function. And in order to guarantee optimality, this H hat function needs to have some properties. And the original properties that people use is known as consistence or monotone heuristic. And the definition is like a little bit recursive. So assume you're looking at two nodes, x and y in the graph. Then you want, and they're connected by an edge. And then you basically want to say that the heuristic at x is smaller than the heuristic at y, plus kind of the cost that connects x and y. And that needs to be true for all pairs of kind of vertices that are connected with an edge. So pretty tricky to verify this, right? And so what people use nowadays most of the time is what's known as an admissible heuristic. And I assume that's also what you mostly have learned in previous lectures. And this one is much easier to define, which basically says that these estimated heuristic functions that we give should never overestimate the true cost to go. Okay, so question for you. What would be the easiest admissible heuristic you can think of? Yep.
I guess it would be distance, like the distance from n to the geometric distance.
Okay, so yes, assuming that the cost we care about is also something geometric.
Yeah.
If the cost is, let's say, time, then maybe not, because there might be, I don't know, a road which has a speed limit, but is shorter, and another road that's longer, and then that doesn't map. But yes, so it's a commonly used heuristic to use the Euclidean distance. What is even simpler? Yep.
You could assume that all costs are the same.
Yes.
Just count the vertices.
Oh, interesting. Count the vertices in the total graph.
I mean, you have the total amount of vertices, and then from the start to middle vertices, just half of all of them.
Okay. That also makes this assumption that the cost is always on each edge at least one, I think, right?
Yes.
Yeah. Which might also not be the case. Maybe let me phrase the question differently. What do you have to do to convert A star to basically just become Dijkstra? Yeah.
cost 0.
Exactly. So really the simplest thing is we know that the whole algorithm only works for non-negative costs. So the lowest possible cost would be 0. If we set our h hat of n at every single node to 0, then it essentially disables our heuristic, and one can formally show that A star becomes like almost a special case of Dijkstra. And Dijkstra was the original uninformed algorithm that only uses kind of the cost to come, not the cost to go. Okay, and yeah, I think in the next exercise, which by the way will be obviously not tomorrow, but kind of in than 8 days, you will also look a little bit at this relationship between the older definition of consistent heuristics and what is more frequently now used of admissible heuristics. Okay, so let's now look at an A star pseudocode and example. Okay, so in A star, we often have two sets, which maybe, I mean, they're always called sets, but I find it confusing because in reality, open is not a set, but a priority queue. And then closed is typically a real set, but keep that in mind. And then we have this funny loop that says, so we start with our open priority queue with our start node. And then in our loop, we first check if there's nothing in our priority queue left. Then we just exit with some sort of failure. Then if that's not the case, we have at least one element, which means that the second step, we can remove a node from this set. And what we remove is the one that has the lowest f value. Here it's called f hat because remember it's this estimate of the true chi that we know and the estimated h hat, which makes it f hat. And that's also the reason why open is not really a set, because if you want to make this operation efficient, in practice you use a priority queue which always sorts the elements by the f value, and then if you take the topmost element, you get automatically this one. Okay, and then you check if n is already our goal node t, then we can basically finish and just report, kind of figure out how the path was and say success. And if not, then we expand the node. And expansion is fairly simple. We basically use our successor function that we had defined before. We check if the element is already closed. That means we are done with it. We don't have to revisit it again. That avoids that our algorithm runs forever. If we would not do that, then we would revisit the same nodes over and over again and potentially never terminate. Then we kind of compute an intermediate or a kind of tentative G value. If that one is better than any solution we have known before, then we update our G value, our F value. I think this one should be technically also the hat version now, so F hat and H hat. And then we have this kind of tricky step, because then we have to check if it's in open, then we have to update the F cost in open, and otherwise we have to just add it to open. Okay, maybe some fun question. What is the complexity of this thing? Yeah.
Like in the worst case, it's linearly into the number of edges we have, right? But like in the average case, this will be one-sided.
Or even your worst case seems to be too good to be true. So, I mean, I guess what you're doing when you do complexity analysis is that you kind of check the loops, right? And you saw, okay, I go through the successors, there's this close thing, so I visit everything at least once in the worst case, and so it's linear. So that's definitely a lower bound, I agree with that. But then to really check if it stays linear, you have to check if each operation in here is actually constant time. So which operations in here are actually tricky? Yeah.
The remove minima to sort the nodes which you put in. Because sorting is like n log n.
Mm-hmm.
Uh,
Exactly. So if we trivially implement this thing, right, and open is a real set, so the way you would do this remove minimal would be you would kind of sort the set somehow and then take the first one, which is at least n log n. And also if you use a priority queue, what is the complexity of a priority queue? Yeah?
Like I think to insert it's log n, but then to look up the first element is constant.
Exactly. Yeah. So this one would be then constant, but then down here you have quite some effort because you have to like kind of sort it into that thing. What about this update? Is that tricky? How would one implement an update for priority queue? Yes?
It will be also log of n.
Uh-huh. But how would it work in practice, roughly?
Like we will like erase it and insert it again.
Pretty much. So you have to find it first, typically delete it, and put it back in, or you do some other fancy operation. And I say tricky because if you want to implement this sort of thing, a lot of libraries actually don't have this operation. So even if you have a priority queue available, it typically has the add and the remove, but not the update. And so you have to find a data structure that supports that, which makes it a little bit challenging in practice to implement it yourself. Okay, and then for closed, you would use typically like a hash set or something, which is very efficient, at least for lookups. Okay, any other questions or comments regarding the pseudocode? Yep.
What's the complexity of the total code now?
That's a good question. I also forgot, but it's definitely not linear. I think in worst case it's something like quadratic, from what I remember. But it also depends on the number of vertices and the number of edges. So it's kind of like this O of cardinality of V times cardinality of something else, right? Okay, but it's a good question. Should look it up. Okay, any other questions? Good, then let's try an example. So here we have this, I think it's the same graph that we have before. The only difference now is that we have costs associated with each edge. And we have our estimated h hat down here that's already given by somebody. So how would we start? And by the way, always how it is down here. What would be the first element in our open priority queue? Okay.
The starting point of S.
Exactly. So we always start with S, and that also means, so down here we have which state to expand next. So we have to look at the successors of S. So how would the open priority queue look then after that expansion step? Like which elements will it have, and ideally also in which order all these elements? Yeah.
I guess S would be removed and N1 would be inserted.
Exactly. So we always take an element out when we expand it, and then we add N1. And then maybe what's also important is that because we added something, our G value updates. So initially we initialize G by infinity because we have no way of reaching it. So the cost to go is infinity. And here's this infinity changed to 1 because the cost from S to N1 happens to be 1. And then if we compute F here, it would be Z1 plus the 2, which is 3. Okay, and so that means we have now still just one element in our set, which means the next element to expand will be N1. And then after that expansion operation, how would our open priority queue look like? Yeah?
And 3 and 2.
And 3 and 2, and in which order? Which one is
So
better?
3 would be looked at first. So 3 first, right?
Okay. So what is the F value of N3 after the operation?
The F value
Uh-huh.
would be
So the G value would be 3, right? The G value is the cost to come, so it's 1 plus 2.
so
And then the F value is plus whatever H says,
F2.
which would be 4. So F is G plus H. We agree that the G value will be 3, right? Because it's cost 1 plus cost 2 for N3.
Sorry.
Yeah, maybe we were talking about a different one. And then what about N2? What is the F value there? Yeah? 3? Exactly, 4. Because we get 1 plus 1 is 2, and then H of N2 is 2, so it's also 4. Which one do we expand next then?
First expand in 2,
Why?
because the local cost estimate is less than 2. Because if you expand N1 to N3, then the cost would be 2, but if you just expand N1 to N2, it would cost only 1.
By local cost, I mean kind of the G value.
Yeah.
Okay. So it's a great observation. So typically what you do is you have some sort of tie breaking mechanism. And there's 2 ways of tie breaking. Like, I mean, there's many ways, but I guess one would be to go by lower G. One could maybe also go by lower H. And one could also break ties by a completely independent mechanism that is more domain specific. Strictly speaking, by the algorithm, it's not defined what will happen. So it would be correct to say either N2 or N3 will be expanded next, because we didn't define how we break the tie. Okay, and I guess on the slide, someone decided to expand N3. And then we already see it here. So now when we are at N3, we have to do the same thing. We expand that. And then I already said which one will be in there. So N3 is taken out because we expanded. N2 still remains because we still had it in the set. And T will be added because it's the successor of N3. Okay, and then we have to make sure that we have our F value straight. So now N2, the F value is still 4, right, like we computed before. What is the F value of T? It is 5, so what do we expand next? N2, very sad, given that we already found a solution. But the solution is suboptimal, so we are not supposed to expand it yet. Okay, so we expand N2, then N2 gets removed from the cube. We get all the successors of N2, which in this case is N4, added. What is the F value of N4? 6. So we have G is a 5 and H is 1, that makes it 6. Exactly. And then of T, it is 5 plus 0, which means the next state to expand is T. And then once we expanded T, we have this check. Oh, if it's the goal node, we return the solution. Okay, fun question. How do you return the solution after you did the search? Difficult. It's just an implementation detail to some extent, but if you never tried implementing it, you might not know how to do it. So who has implemented A star before? Okay, just one person. Trying to remember how it worked. Yeah?
I guess you could return like a sorted set of edges, like of the edges.
But where does the sorting come from? Basically, what we kept track now is we have all the G values and all the H values, right? And we know we somehow reached the goal. But we now need to, typically what we're interested in is what's highlighted in red, this like complete path. So sorting the edges makes sense, but how do you exactly sort it?
If there's a way to know the predecessors, you can always return the predecessor with the lowest G value.
Exactly, and how would you have this information?
I mean, I have it in the sense that I know every edge. So if I know
Yeah?
And manually include this in the priority queue somehow in the stack structure, the predecessors?
Exactly. So typically, instead of only having the G, which you already keep track of, you have something like came from that always keeps track of it while you expand, right? And then in this case, if you have to kind of check if you update a node or not, then you might also need to change it or not, right? But in principle, that's what you do, and often in the pseudocode, it's not included. Okay. Why am I so picky about it? Because I think in the exercise you are asked to implement it. So it makes sense to know about some of the details. Okay, good. Then we can talk about the optimality. Do you have any questions before we dive into that? All right. So just to recap, we have these 2 or 3 properties. One is that A star is complete and optimal, which basically the completeness meant it will return a pass if it exists, and a failure otherwise if it doesn't exist. And optimality means that saying it returns is the lowest cost. What I find confusing is that at least in this old paper, this property is also sometimes called admissibility, which is, of course, different from the admissibility of a heuristic. So I try to stick to just complete and optimal for just clarity. And then what we don't discuss that much is this optimal efficiency, but that's also important. Okay. And then, as I said, this is based on this original paper. So what they did is that they had 2 helper lemmas, and then finally one theorem showing that A star is complete and optimal. And we will just try to go through these steps. So the first statement that we're trying to show is that A star always keeps a node in the open set or priority queue, which is on the optimal path. Then the second statement is that we use that H is admissible, and then that we have this true underestimate of the cost F. And then we use those 2 statements at the end to finally show that we have completeness and optimality. Okay, so let's first start with this first statement. So the statement that we want to show is that A star always maintains at least one node that is part of this optimal path of P inside our open priority queue. And so graphically speaking, we see it here. So maybe we have this optimal path is highlighted in red, and then this thing is the open set, and we want to make sure that at least one of these 4 elements is always in the open set. Okay, and as it goes with these kind of fun old papers, it is kind of a more or less direct proof where we try to enumerate all the possible cases and convince ourselves that in all of these different cases, the property is fulfilled. So let's start by assuming that we have this optimal path that is known to us, and we just call it like n0 and 1 to nk, and because it's an optimal solution path, the first node in the graph needs to be S, and the last node in the solution in the path needs to be T. Then the easiest case is that we just still have S in our open set, which you can imagine as being the case in the very first iteration of the algorithm, and it's guaranteed to have S. Because it's S, we know that the cost to go is 0, and that means our estimated g function, which is the true cost, is also 0. And therefore, we have this node that is also in P. Okay, and then the second case is the actual only interesting one. So now we assume that S is not an open, and we want to show that any of the other ones basically is not only an open, but has this correct cost estimate. Okay, and then what we do is that we try to look at the closed set. And remember, the closed set contains all of the nodes that we have visited already. And then we take from the closed set a subset that has a solution path P, and we sort it by that index. So in other words, we find kind of the furthest point on the solution path that we have that we already visited. Yeah? And that could in principle also be S, right, if we already visited S. And then we take the largest index just because we only care about the latest one in our sequence. Okay, and since we took that from the closed set, it definitely has been expanded. And because it has been expanded, we also have already considered some sort of successor nodes. But these successor nodes now have to be in the open set, can't be in the closed set. Because if they would be in the closed set, then this subset we looked at wouldn't have had the largest index. So we have something that is on the optimal solution path, but that's still an open. And because that is the case, we have a successor node that is an open, then we can also reason that our kind of estimated G function in open still has a value that is correct with respect to optimality. Okay, and so this kind of proof is basically in structure a proof by induction, right? Like we have the beginning of the induction, and then we have this other case where we increment the index. And then we can show that this hypothesis is correct. Even though in the paper they didn't explicitly write it like that. Okay, any questions regarding that statement? All right. The second one is, I think, a little bit easier. So now we take into account our heuristic functions. So the first one was really just about the G-score, right, which we can directly observe. Now we have to use the admissibility of our heuristic function. And we want to show that if we have a heuristic function, that it is true that we never, that there's always a node that is an open that also has the F value that is a correct lower bound. Okay, and so this one is also again direct. So we use that first statement that we always have some node that has the correct G value that's still part of the solution. And then we put it into that definition that we had of the F value, the estimated one, is our estimated G values that we computed, or the optimal G values that we computed, plus the estimated H value. And then by lemma 1, we can basically replace this hat, which is the true optimum, with the things that we kind of explored while we ran our A-star algorithm. And we get this equality. And now we know by this assumption of admissibility, all we do is we now replace the H hat with H. And because we have the inequality here, we get an inequality here. And then this thing is nothing else but the definition of our f function of n prime. And then by our assumption that because n prime is on the is like a part of the optimal solution path, all the f values there should be the same, right? It's always g plus h. So that one is also the f value of s. And then we can basically show that we always have this under approximation of the estimated f value of n prime with respect to the true cost f. Any question about these proofs? All right, then we just kind of bring it together. And this proof is, yeah, I mean, this part is, again, a bit weird because it has all of these cases. So it tries to do a proof by contradiction. So let's assume that we kind of terminate and we don't return the optimal path. And then we show that this can't happen. And yeah, these cases are a little bit silly, but it basically says, okay, if we can't terminate at a not goal node because the only time we terminate is like by the definition in the pseudocode, either if the open set is empty or if we reached the goal node, right? So the only interesting case is now the one where we terminate, but somehow we manage to report a result that's not optimal. Okay, so we kind of, because it's a proof by contradiction, we assume we terminate, but somehow like the f value that we found at the end is larger than the f value of the start value, so like the true one. So the one we found for the goal node is larger than the optimal one from the start node. And then we can just directly plug in lemma 2, and we basically show that this is not possible because there must have been some node before in the open set that we could have expanded instead, and if there would have been another expansion with a lower cost, we shouldn't have terminated, and that's the contradiction. Okay, any question about the proof? The proofs are kind of annoying also for teaching. Maybe it would be better on the board, but at the end of the day, it's best to go step by step. Again, if you have trouble following it with the slides, and if that's too complicated, you can go to the paper. There are a few more intermediate steps that's a bit more wordy than this to follow it. And of course, you can ask questions. Okay, then do I have some? Okay, let's first finish this part, then I have some questions for you. So it's optimal and complete, which is also known as admissible. What we have not touched on today is this optimal efficiency. That's also a pretty old paper, and you can look at that if you're interested to see how that was shown. What's important in terms of this lecture is that because there's no provably better algorithm, like we typically stick with A star and variance, because we know there can be nothing better under these assumptions. What you can do better is, of course, having a stronger heuristic function or using different classes of algorithms or changing some of your assumptions. So if you don't care about optimality, there might be, again, better algorithms, right? Okay, then some questions for you. Will A star always return a unique solution?
With unique, you mean always the same solution?
Yes.
Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. Yes. With unique, you mean always the same solution?
Yes. Okay, good point. So let me clarify. So I assume same heuristic, yes.
Could be that there are two optimal solutions, and then, like, depending, for example, on the tiebreaker, we could find another one first.
Exactly. So it's important. I mean, we always talk about optimality, but there could be quite many optimal solutions. We will just guarantee to find one of them. Which one is unclear, depends on almost implementation details. In principle, A star is of course deterministic. There's nothing weird in here, but sometimes these data structures we use are not necessarily deterministic, right? Like, for example, the priority queue, if you do not explicitly define how to do the type breaking, or if your type breaker also ties, which is possible, then which of the solutions you return is unclear. Okay, what would be the best possible heuristic? Yeah,
The heuristic that, according to our cost, represents the true cost to the goal.
exactly. So we can underestimate it, but if we have the equality sign, that would be the best. How? Maybe that's already the next part. Okay, so we know this. Okay, then let me continue. Then I might have more fun questions afterwards. Okay, so admissible heuristics. Maybe what's important is that these heuristics, they're very classic and very old, and we talk about it, but they come to you in many different places. So for example, in optimization, you often use these sort of things as lower bounds to try to limit the search space you have to optimize over. And in other search problems, these sort of heuristics, like if you think about like game theory and alpha-beta pruning, for example, heuristics can help you to just prune away many nodes in your search and help you to find solutions faster. So heuristics are super important, and one big question is obviously always how can we find it? And it's still today often an open research. And so one classic approach is to just try to solve a simpler problem, because then that is basically underestimate. And so what would that mean in motion planning? What would be a less constrained problem that we could solve? Yeah.
One without obstacles.
Exactly. And if you really remove all obstacles, what would that mean for geometric planning? Which heuristic would you end up with?
Totally free space.
Yes. And which function?
The Euclidean distance.
Exactly. Yeah, the Euclidean distance that we already had. Of course, you can also go in between and just say, maybe I only remove one obstacle that's difficult, right? That would be also valid. Another option would be to just shrink obstacles, which you could do by maybe using simplified shapes that directly go inside, but where then collision checking becomes maybe much cheaper. If you're in manipulation planning, what you could do is you just remove joints. So instead of really reason about the full hand and all the fingers, maybe you only consider 2 fingers. It's a relaxed problem. As long as you solve the relaxed problem optimally, it should be a valid heuristic. Okay. And then another option is to just use these pre-computed motions, and then, I mean, this one is then tricky to guarantee that it's really a lower bound, but it's also possible, and you can find some in the paper. Which brings me maybe to a very interesting question. What happens if you have a heuristic, but by accident it is not admissible? What does it mean for A star? Yeah.
Maybe we don't find the optimal solution, or if there's an optimal solution, we are unable to find it.
Uh-huh. That's best case scenario, I agree. So all the guarantees are gone, and then we might spend even too much time, because you always have to think A star does two things. It computes a solution, but it also computes, you basically implicitly prove that the solution that you get is optimal. Now, if you give it a heuristics that's not admissible, you spend a lot of effort constructing a proof that's incorrect. So that doesn't really make that much sense. Maybe another fun one. How can you combine A star with machine learning? Yeah.
Could use machine learning to find our heuristic, as long as we make sure that it's not that it stays admissible, so it doesn't overestimate.
Exactly. But how would we do that? No idea. Right? I also don't have any idea.
In the simplest case, you could just like flip the range of values it can return to some other heuristic or some.
Okay, fair enough. So you query a neural network, and then you have a secondary heuristic, and you take the minimum of the two. Yeah.
Maybe like if we use machine learning for a heuristic, we can like while training the model, we can like verify by using A star with another heuristic that it's definitely admissible to make sure that like the machine learning one is also admissible.
Okay. So I see. So during the training process. Yeah. Okay. And I think kind of next week we will touch on some extensions of A star where it's a bit more obvious how learning can help to improve the search, right? But directly A star, it is indeed tricky because of this admissibility requirement. Okay, so to summarize, we looked today mostly at stuff that you have maybe heard before, like the A star algorithm. How can we use it on graphs? How do we construct graphs on a high level for motion planning problems? And then maybe what was a bit newer to you was kind of the properties of A star and how we can formally show these. And we dove a little bit into admissible heuristics, but we will have to see some more examples next week. Yeah, and if you're interested, there's this class by Maxim Likachev, who's basically the guru in search-based motion planning. So he has a lot of material on just this sort of search-based stuff, which you can look at. The A star paper where we took out also the proof today. And if you want to know more about the heuristics, this other paper by Pearl. All right. Any questions? Then thank you and see you in 1 week. No discussion tomorrow.